All right, folks. We just did this example where we pulled this loop that way at speed v. I'd like to do something different now, introduce a new concept. The same setup, but now we have the current as a function of time. We're not going to move the loop. Loop still has width A and length B, whatever, height B and width A, and is sitting a distance C away from the current. So our B is equal to mu naught I over 2 pi x, and x is the distance to the area element. So the flux is equal to the integral of mu naught I over 2 pi x multiplied by b dx, and that's going from C to C plus A, and that was going to give us mu naught I over 2 pi b ln of C plus A over C, right? So what's interesting in this case is that you have the following. You have this. You have mu naught I, okay? Mu naught B, sorry. Mu naught B over 2 pi and ln C plus A over C multiplied by I as a function of time. Now in this case, what I'm going to do is the current is a function of time. Let's say I is equal to I naught sine of omega t, or whatever. Let's say, so I is equal to I naught sine of omega t. Let's say that that's the case, okay? So what I'm trying to introduce now is the following concept. We have a flux. See, this is the flux in object 2 from object 1. This is object 2, and this is object 1, okay? And the epsilon induced in 2 from 1 is equal to negative d by dt of the flux in 2 from 1. So that's equal to negative d by dt of this. So what this ends up being is, well, ends up being, minus d phi by dt. So minus mu naught b over 2 pi ln of C plus A over A, and that is d by dt of I. Okay, so now we have something interesting here. We have the epsilon induced in 2. This is object 2. Epsilon induced in 2 from object 1 is negative d by dt of d phi 2 in 1. So d by dt of phi 2. Phi in 2 from 1, right? So this is what? This is I1, right? Okay? And we have an interesting concept now that we have an induction, something being induced from another object. We have a mutual induction or something called the flux linkage, right? So epsilon in 2 from 1 is d phi in 2 from 1 by dt, okay? And it can be written as epsilon in 2 from 1 equal to m in 2 from 1 multiplied by di by dt, okay? All right. Alternatively, what you can say is the following. You can say that phi in 2 from 1 is equal to m multiplied by I1, okay? M to 1, or mutual inductance, right? So either or will get you the same result. So we're talking about mutual inductance here in this case, right? And we are going to expand this idea a little bit now to talk about the meaning of self-inductance. I'm not sure how much of this to test you on, given the circumstances, but I just want to get across the idea that the mutual inductance is given by the flux in 2 from 1. What you can say now is the mutual inductance in 2, between 2 and 1 is equal to phi in 2 from 1 divided by I in the 1, right? All right, so moving on, there are some examples that I'll do for you here, and some examples that I'll just post for you having been done, right? Solved examples and problems and stuff like that. You know, as much as possible, we're relying on these videos to get the material across, but there'll be some things that we have to pass on to you in you know, other formats as well, right? Okay, so let's say that now you have a solenoid, right? And this is an ideal solenoid where the field was given by B is equal to mu naught and I, okay? And what's really interesting now, just on the side, should talk about that now maybe, is if you have a solenoid with current I flowing in it, you have some sort of power source powering this thing, and if you were to wrap the solenoid around a piece of iron, for example, okay, what do you think the field will be in this area, in this region? The field inside will be given by B is equal to mu and I, okay, and mu is, okay, and what is N? I'll remind you of what N is. Mu naught is the permeability of free space, N is the number of turns per unit length, and I is the current flowing through here, okay? So that will generate a magnetic field, let's say, going this way, right? And this is B. Over here, we have this, now if you have this is an iron core, a piece of iron bar, right? What happens when you put a piece of iron bar in it? Well, the magnetic field in the area and the solenoid becomes equal to mu and I, and mu is equal to a mu r, a mu naught, okay? And please look up, for example, what the relative permeability for iron might be. What is that doing? It's large, so you know, it can be many thousands for mu r, and what that gives you is a huge magnetic field in the area. Basically what happens is the domains line up to help you, to give you a stronger magnetic field for some materials. So look up iron, you know, see how much advantage you get by putting a piece of iron inside this. This gets us in a discussion about magnetic materials and magnetic boundary conditions and B versus H as opposed to D versus E, you know, flux density. We had D and E in electrostatics and boundary conditions. We have boundary conditions for magnetism as well. Those are in the notes as well. Please look them up. We won't be having, you know, won't be covering them in the course, but it's something for you to look at. They become important, these boundary conditions, for when you have, for example, waves going from one medium to another. Right? You have electric fields, or, you know, electromagnetic radiation going from one medium to another through an interface. How the electric fields and magnetic fields interact with the material at the boundary affects the propagation of the wave. Please do look that up, and if you're really interested in that, look at the Fresnel equations, Fresnel equations, and look what happens to phase shifts as rays get transmitted versus reflected, depending on the angle and whatnot, depending on the media, and indices of refraction. And it's all a very interesting discussion that you can tap into. Okay. So let's say now that this current going through here creates a magnetic field, right? And now if the current is a function of time, okay? If the current is a function of time, what is the self-inductance of this solenoid, okay? Well, you know, what do we say? We said that epsilon induced is equal to d phi by dt, okay? D phi magnetic by dt, okay? And we had an expression for mutual inductance as phi in 2 from 1 divided by I in 1. This now, we can say that the self-inductance, guys, of this object is, let's take a look at this. Let's take a look at what this gives us. So let's say I is a function of time. Okay? So what is the flux? Well, the flux is equal to what? You have, it's equal to the field times the area, and now the flux per loop is equal to the field times the area. But now you have so many loops in here. You have a total, of n loops overall, and the total flux is equal to what? The total flux is equal to n times the flux per loop. So d by dt of n times the flux per loop, okay? And that's equal to d by dt of, okay? Let's say I is equal to some I naught sine of omega t, okay? Okay? So d by dt of, well, n, right? And the flux per loop is equal to b times a. B is equal to mu naught ni, and a is a cross section of the solenoid. A. So that looks like now n is n, okay? And you have mu naught, and you have little n, and this is a times di by dt. And you can write this in one of two ways, because what is n? N is little n times L, or little n is big N over L. Remember that n is, so let's say this has a total length L, okay? N is equal to the number of terms per unit length, right? Or n is equal to little n times L, right? So either way, it will be a square in there. So let's say you want to write it in terms of little n, that's equal to then mu naught n squared, mu naught n squared times L A, right, times di by dt, okay? So now, in this case, we have epsilon induced equal to this times that. So what I'd like to focus on is the following, okay? We can say that the self-inductance of the object, okay, L, self-inductance, is equal to epsilon induced in the object divided by the rate of change of current in the object. And in this case, the self-inductance for this guy is equal to mu naught n squared L A, and that's your self-inductance for a ideal solenoid, right? So we have just discussed mutual inductance, and now we're talking about self-inductance. You'll notice also that L is equal to, nothing wrong with saying it is phi in 1 from the current in 1. That'll give you also the same result. So either or. This is a bit easier kind of calculation in that you can calculate the flux in the object divided by the current that caused that flux, be it the self or be it a mutual inductance, and you can define the inductance that way, divide the ratio of the flux divided by the current. Okie dokie. All right, I think we'll pause here.